Okay, continuing on from the multiple explanatory variables in the Cox proportional hazard model, in this video we're going to be focusing on the interaction term. What is it and how do we interpret the coefficients? You don't need the book by Hosmer and Lemeshow, first edition, but this is the example I'm using. And here's the model. Three models. We're going to recreate table 4.10. So we're going to get the coefficient, that's a coefficient of the log of the hazard, and then E of the coefficient, which is the hazard rate. And we're going to do it for three models. One where the explanatory variable is treat, which is binary indicator variable, 1 if there's treatment, 0 if individual did not receive treatment. And then the second model is called the adjusted model because we're going to adjust treatment for age. Okay, so controlling for age. And then finally we're going to and age is continuous. So note that in this model we would have a categorical explanatory variable and a continuous explanatory variable. And then given those two, and if we limit ourselves to those two, the biggest model that you can have is the one including what they call the interaction term. When you have indicator variables, or otherwise known as dummy variables in your model, basically we have more that, although we've got one equation for our model, in that model there are submodels. Okay, so it's like we're running more than one regression in one go. So this, if we look at the adjusted one, this model here, because treatment is coded 1 and 0, so there will be one model if we set treat to 0, which we can write out, and there'll be one model if we set treat to 1. So similarly, when we have reached here, we can see that there are going to be two models. Okay, the focus is on looking at this guy, testing is it significant, and then we're going to interpret it. Okay, ready code here. Now because we have some missing values, I'm going to use the data where we've got complete cases, so basically there's no missing observation per row, following the book. And then we'll run the first model at this Cox pH model where we have treat. Oops, that's because I didn't do survival. This is something I keep forgetting. Library survival. Okay, up arrow, rerun it. Okay, and then I'm showing you how to be a laser here. I just want to look at this guy, just copy paste there. And I've got the coefficient, there it is, and that's the E of the coefficient. Now, I've never tried this. Can I copy and paste this straight into Word? Excel, sorry. Oh, well, no, it won't work exactly because oh, let's not get involved in that. Sometimes shortcuts do not tend to be short. Okay, that works. Next, so let's just complete this. I'm just focusing on the coefficients here for now because I want to know how to interpret them. But of course, in real life analysis, we're not simply interested in coefficients. We're interested in tests, hypothesis tests. Okay, next, second one, the adjusted model. Adjusted is just the name that the book gives it. It's not like a formal word for it. Adjusted is not standard jargon, as long as I know anyway. Copy, paste that output, and here you go. and same as the book, yes. So let's just transfer these guys over. So while I'm doing this, let's refresh. The coefficient here represents the coefficient of the log of the hazard, which is not very interpretable. What is log of a hazard? Whereas the e of the coefficient is the hazard rate, or you could say it's the risk, instantaneous risk of the event happening. Okay, there you go. And then finally, let's run it with the interaction. This is something I did in the previous video, but I just mentioned it very briefly at that time. What we want to run it with both explanatory variables and times, which literally means multiply. So you take for each individual, take their treat figure and multiply whatever their age is at the age of at the time they entered into the trial, and then that'll be a figure, that'll be a value, right? And we do that for every single row. That's what that says. And now, how do I run that? Well, the shorthand way to do it is to say age times treat times age, or age times treat. It means the same thing, right? Treat times age or age times treat means the same thing. You get the same output, doesn't matter which way around you do it. And this is shorthand for saying include all the terms separately as well, or in other words, all the lower order terms. If you've heard about hierarchical model, that's what this means. It means that include all the lower value terms. So we do that, and then look at it. There you go, nice stats. In case you're wondering, yes, you could take hold of this guy just to get exactly the same output. You could do it longhand by writing out in full, because what we've got here is treat age, and then this colon means the interaction, means times when we our notation. So treat times age times treat, doesn't matter. Likewise, doesn't matter which way around we've got these two, age plus treat or treat plus age. Try it. Okay, you see exactly the same. So let's transfer them over, and this time let's speed things up. Okay, so here's the completed table just for the coefficients bit. This allows us to review quickly what we did last time. Confounding variable. Let's compare the crude to the adjusted. Notice that the coefficient on treatment is about 0.22. When we include age, it changes only by a small percentage. It's like, very small. So that indicates that age in here is not a confounding variable. We're going to omit the interpretation of the coefficients for this model because it's just the single explanatory variable, which we've done before. So let's look at this guy. As I said at the beginning, any model where you have dummy variable encapsulates within it more than one model, where the number of models equals to all the possible values of your dummies, or combination of dummies. So here we've got treatment, and let's just make a note here. Treat equals 1 or 0 for each individual. So imagine, each individual takes a value 0 or 1. It has the treatment, which is coded 1 or 0 otherwise. So let's write down the models. Say we had treatment. So a person who has treatment is coded 1. So I'm going to write down here the model for treatment. This says that the hazard function, let's denote it by h, hazard function is equal, and then it's equal to the baseline, which is something, say h0, which we don't care what that is, times the function g, which depends on the explanatory variables. So it's this function g that I want. Alright, so let's take this out from the book. So I'm looking purely at the function the part which does not depend on the baseline, and that is equal to minus 0.233 times treat. Now the value, let's put treat. Actually, let's take this out. I'm going to do it generally. Treat, and you just read down. So and then minus 0.0133 times age. Right? Without by convention, if we just in math, if we just don't do times, if we don't leave a space between the number and the variable, that just means times. Okay, so that's the general for this one. That's the general model. But if treat is equal to 1, so there's two types of individuals here, imagine. Treat is equal to 1, then the model G becomes minus 0.233 times 1, which is the number itself, minus 0.0133 age. Okay, and the second type of individual has not had treatment, so it's coded 0, and then that person's hazard rate is, but treat takes the value 0 now, so that disappears because 0 times the number is 0. So here you've got two models. Okay, now let's look to interpretation. If we look at the interpretation of the age, those coefficients of whether you had treatment or not, same coefficient. In other words, the impact of relationship of age to survival, time to event, is the same. And it's interpreted like this, like before, only now we've got to take account that we're controlling for something. This says that irrespective of whether the individual has had treatment, an additional year in age will reduce the risk by about, it's 1 minus this guy here times 100, so it's about 1.3%. And the risk is of taking drugs, start taking drugs. The treats coefficient here, it says that having treatment reduces the risk of relapsing back into taking drugs by 20%. That is irrespective of how old they are. So you're saying that this treatment program, if you put somebody who is 20 years old and put somebody who's 60 years old in the program, once they've had treatment, their risk of relapsing back into drugs falls by 20%, and that might be questionable because you might think that age will have something to do with it. In other words, age as well as treatment combined together will determine this time to event, or the risk. And that kind of motivates the final model, because this interaction term is exactly allows for that, the combined effect of treatment and age. So that term there could say something like a person who is older, if they had treatment, would have a different impact to if a younger person had had treatment on the risk of them relapsing back into drugs. And in applied work, these interactions are interesting. As before, we can have there's two models in one here, because treat takes the values 1 and 0. And I don't want to write all the model out again because I don't know how helpful this is. It looks a great big mess. Delete. The interpretation of age and treatment is the same as before, same as this. Basically, you are looking at the impact of that variable controlling for the other thing. Okay, so we finally got this guy here. Right, well, we know that treat can take the values 0 and 1. For a person who has not had treatment, what will the variable take? What value will it take? It'll take 0, because 0 times any age number, finite number, is going to be 0. So that will disappear for a person who has not had, who has not had treatment. So in that case we only got these two, in which case this is the model. For a person who has had treatment, you can see then that this value of treat will be 1 times age, so that's age. So this is where you got to think back to your maths days. This is like adding like to like. So here you've got treat, age, that takes this much, and you'll have another age here that takes this much. So the combined age will be this plus this guy, equals to, can I do that? Yes I can, plus this guy. So your new age variable is this guy. Alright, and then what would the hazard ratio be? It would be E of this number. Note carefully that we do not add the E of the coefficient for age and the interaction. Would not be this number, would it? Okay, now to the interpretation of the coefficient on the interaction term. This coefficient, E of the coefficient, is less than 1. So it tells us that for an additional age in the person who has had treatment reduces this risk of relapsing back into drugs by around 2.3%. In other words, it falls, and it falls by about 2.3%. If we can do it without numbers, what this is saying is that for an older person, the older you get, if you put that individual on the treatment, that's going to be more beneficial to them, in that it reduces the risk of them relapsing back into drugs. So let's make the distinction. The coefficient in age here tells you what is the impact on the risk given that an individual gets older by a year, and that's irrespective of whether or not that person is placed on the treatment. This coefficient here, the interpretation of this is the impact on the risk for an additional year in age, but for when the individual is on treatment. That's the interpretation. Now this could get, I could stop the video right here because this is getting rather long, but I just want to kind of finally, well, let's do a final thing, is to say, alright, so we've done the interpretation of the coefficients, but I want you to know that usually you do not, you won't report these unless the model satisfies all the assumptions, which we'll come to in the later videos. One of these things we need to look at, one of the tests we need to look at to see whether these coefficient is significant or not. Significant from 0. So we'll look at the interaction term here, and the z value minus 1.6 with the corresponding p-value, which is 0.1. Remember, p stands for probability, 0 to 1. If it's small, that means we reject the null. If it's big, we do not reject the null. And it's big. It's bigger than 0.05. So we say that this coefficient is insignificant. So out of the 3 models, what would you do? Since you look at this guy and you say it's actually insignificant, that means what the interpretation we've just done there is actually not very meaningful, because the effect is that coefficient is not actually different from 0, the true coefficient. So what we would do is we would run this, and then we'd check to see whether both of these guys are significant. Have I got the output? No, where is it? And what you find is that time age, what you find is that it is significant. Okay, they're both significant. Some people call this alright, let's just say this they're both significant. So out of the 3 models, which one would we pick? We would not pick the interaction one, because the interaction term is not significant in this case. even though it's got a nice interpretation there. It would be a test between this one and this one. Now this is where, if you've got edition 2, a bit interested to what you have to say about what the book says, because I only got edition 1, and for some unknown reason the book says that statistically that the interaction model is the best, looking at this guy, and it's used the partial likelihood ratio test, which is fine, but the interpretation of it is not fine, because what they tell you is that the partial likelihood ratio test comparing age-adjusted model to the interaction model is G equals 2.57. That doesn't mean anything to me, but I want to know what the p-value is. P-value is 0.1. Now, know with this partial likelihood ratio test, the null hypothesis is that the smaller model is like adequate relative to the bigger model, and the alternative is that the bigger model is adequate. If I can say it in layman terms, null means go for the smaller model, and alternative means go for the larger model. Yeah, where the small model is contained or nested within the larger model. Well, if the p-value is 0.1 for this test, that means it's big, so we do not reject the null. And if we're comparing these two models here, and if you're telling me that the p-value is 0.1 for the test comparing these two models, it means that the additional term that you added is not significant. So basically, it's the same as saying we pick the smaller model. Remember what I said about that test, partial likelihood ratio test? The null is that we go for the small model. Well, this model is smaller than this. Smaller in the sense that contains fewer variables and therefore fewer coefficients. Okay, that test is very useful because it's always works like that. Partial likelihood ratio test. Null is that the smaller model is better. Alternative is bigger model is better. Right. I have some more code here. What is this about? Oh yes. Just out of your interest, if we run this interaction model, we know it's not the best one anyway. We can see that the new coefficient on the new age is going to be the sum of these two, this guy. But how do I know whether it's significant or not? Because it's like a new coefficient. It's like a new coefficient, sum of these two. See, how would you do the z-test? That's what I'm saying. Well, how you can do it is by, and I've got code here, is by running a subset of regression, because essentially what it is that you're just doing it with the covariate of explanatory variable of age for treatment 1. So what you do is you use a subset command to extract out all treatment 1s, and then what you do is you run the regression. Just now on the survival object on age, where this age is only now for people who have treatment 1. Okay, and then we look at it. Here you go. So now don't be surprised that value is not exactly the same as this value. Okay, but look at the value here. And in this case, you can see it's significant, but then the interpretation of the age here now is for the subpopulation, for the people who did take treatment. This gives the interpretation of the age on the hazards ratio for this age. In the book on page 134 at the bottom there, it's got the z there, which is 2.41. We've got minus 2.53, it's similar. That 2.41 should be minus 2.4, not that it makes difference to the p-value reported there. They report p-value 0.016, we've got 0.012. Anyway, leads to the same conclusion. Okay, so a long short of it is that the interaction terms are very interesting.